Now, I noticed a very important confusion in some of you, which needs to be clarified at this stage. I said that if you have a fixed point and if you locally linearize it around that point, you get a equation of the form x n plus 1 is equal to a x n. And we said that if the eigenvalues of the A matrix are real, then there would be, depending on the magnitude of the eigenvalues, there will be some expanding direction, there will be some contracting directions. Now, I notice that some of you are confused whether the eigenvectors would be orthogonal to each other. In the exams, you found that they are not, right? You found that they are not orthogonal. But then I had commented that if you any given region is stretched in some direction, contracted in some direction. So, as a result, if you start from a circle, what will be the result? Will be an ellipse. I guess the source of the confusion is that the ellipse has a major axis and a minor axis, and the major axis and the minor axis are orthogonal to each other, right. So, that is probably what led to the subconscious idea that what we are looking for are orthogonal eigenvectors. No, that is not true, but it is still true that a matrix times a circle is equal to ellipse. While studying matrices, we often do not realize this geometrical concept, but it is true. Any matrix operated on any square matrix operated on an area of a circle, operated on a circle means operated on every point of the circle, leads to another shape which is an ellipse. So, what is the problem? The issue is that here you are starting from a circle and here you are ending up in an ellipse. There is obviously an expanding direction and a contracting direction, the major axis and the minor axis, and obviously except for a few cases you do not expect the eigenvectors to be orthogonal to each other. Only in symmetric cases they will be, else not. That is why we need to recall a theorem that probably you have come across in mathematics classes, but it will be necessary for us to recall the theorem. The theorem says so, n is an unit disk, a circle in the space of real numbers of dimension m, and let A be an m cross m matrix. Now, this is the important thing. Let S1 square, S2 square, Sm square be the eigenvalues and u1, u2, um be eigenvectors of the m cross m matrix A transpose. This is important. Then u1, u2, um are mutually orthogonal and 2 the axis of the ellipse A operator on n are S I U I. Notice what it says. First, what are the axes of the ellipse? They are the eigenvectors of not the original A matrix, but A transpose. The moment you take A transpose, the eigenvectors of this matrix would be orthogonal to each other.
For any symmetric matrix,
Any?
For any symmetric matrix, the eigenvectors will be orthogonal.
Yes, but since A could be just any matrix,
A transpose is a symmetric matrix.
you need to get it into that form so that you get orthogonal vectors, and that is exactly what it says. But in addition to it, that it says that the contraction or expansion along that direction would be square root of the eigenvalues. The eigenvalues are S1 square, S2 square and all that. So, suppose you got the eigenvalues, then whatever was the radius of the circle in a particular direction, say from here to here, it was say r, and suppose this is one of the eigenvectors, this, that means eigenvectors of A transpose, then if I ask you how much will be the contractivity or expansion along that direction, it will be given by the square root of the eigenvalue in that direction times r. Okay. So, essentially when we talk about the ellipse and when we talk in terms of a circle turning to an ellipse, essentially we are using the matrix A transpose. What are the implications? The implications are, okay, now is that clear that if you obtain the eigenvalues, eigenvectors of the original A matrix, they could be non-orthogonal, just any directions. But the moment you take A transpose, they become orthogonal and they are the actual directions of the major and minor axis. So, let us illustrate that with one example. Suppose the A matrix is, you do this, 0.8, 0.5, 0 and 1.3, simple. So, you can obtain the eigenvalues and eigenvectors, just obtain that. Can you tell? 0.8 and so obviously this will be a saddle fixed point because there is one eigenvalue outside the unit circle. What are the eigenvectors? For this one it is and for this one no, yes, no, 1 1. Since you are able to obtain this, so I am not explicitly doing this here, but you should be by now quite comfortable with these calculations. No, you might take -1, so what? The other one will also be -1 then, because this is just a direction. So, what are these? 1 is 1 0 will be along the x direction and the 1 1 will be these are the two directions, and in these two directions you have, in this direction you have expanding behavior and in this direction you have contracting behavior. Now, if you start from a circle, where will the next iterate of the circle lie? Next iterate of the circle will not lie along this direction, obviously, right. Its major axis will not be along the ultimate expanding direction. Ultimately, what will happen if you keep on applying this map on this circle, keep on, then ultimately it will expand along that direction, all right. But when you come to the question of this, the ellipse that you obtain in the next iterate, it is not along this direction, it is along the eigenvector of A transpose. So, obtain A transpose. A transpose is we okay. This theorem has said that if you apply the matrix on a circle, the result will be an ellipse, but that ellipses major axis and the minor axis will be along the eigenvectors of the matrix A transpose. And since the eigenvectors of the matrix A transpose are not the same as the eigenvectors of A, therefore, you cannot do this. You cannot say that it will turn into a ellipse looking like this. It will not.
Sir, shouldn't the maximum expansion be along the direction?
It will not be, because the contraction is along this direction. Okay, the contraction is not along this direction. Contraction is along this direction, and therefore, in actuality, it will be something like this, right? And so, you need to know what is this direction, and that is given by this matrix. So, let us you open it. How much? 0.89, 0.65, okay. So, what are the eigenvalues and eigenvectors of this fellow? So, we start from here. Here is A transpose. Its eigenvalues are yes, 2.05 and 0.5, 6 or 7, something like that. Okay, fine. And what about the eigenvectors? Now, the eigenvectors will be orthogonal to each other. So, obtain the eigenvectors. Why don't you bring calculators? Then this becomes simple. Okay, let me put the values and you check whether I am writing the right thing. right. So, these are obviously orthogonal to each other. So, if you start from the ellipse, from the circle, it will turn into an ellipse with these eigenvectors. So, this eigenvector, how do I draw? This is 0.8 something. So, say we give the point, it will be up there and no, this way and down like this. This will be one direction, and this will be another direction. Okay. And so, this will be expanding along this and contracting along that. So, this is the ellipse that you get, and these are the major axis and minor axis. Now, you might ask, what is the relationship between this and the eigenvector of the original A matrix? The idea is that in the first iterate it will fall along that, all right. But then if you ask, what if I apply the same original A matrix on this ellipse, you will get another ellipse. Again, if you apply that, you will get another ellipse, and so on and so forth. Ultimately, what will happen? It will turn into a thin, very elongated stuff. Elongated in what direction? Along the original lambda this direction of the original vector. Is that clear now? Okay. There are certain not so intuitive things, counterintuitive things that result from this. For example, if you have both real and equal eigenvalues, what will be the behavior like? Then there is only one eigenvector, and if the eigenvalue is less than unity, you expect it to contract along that direction, right. Okay. Now, let us try to do this on a problem. Say A is equal to if you have this, then what are the eigenvalues and eigenvectors? 2 by 3 and 2 by 3 and 2 by 3 repeated eigenvalue, and the 1 0, right? Right. But then you will not be allowed to conclude that it will, in the next iterate itself, it will have the ellipse with a x axis, 1 0 is the x axis, as the major axis. It will not happen. You will have to obtain A transpose and its eigenvalues, eigenvectors. Do that. So, this is what we had with A only. Now, A transpose what do we have the eigenvalues and what do we have the eigenvectors. Are you getting something counterintuitive? The eigenvalues? Yes. What is the eigenvalue? 1.49 and
0.39.
see, 1 is greater than 1, which means in the next iterate a circle is going to expand in one direction, even though your eigenvalue was less than 1. It is a very counterintuitive situation that really happens. And so it means that if you start from a circle, in the next iterate, what are the eigenvectors? Suppose these are the eigenvectors, suppose of this matrix. That means we are talking about the major and the minor axis. Then it is going to expand in one and contract in the other in the next iterate. But since the eigenvalues of the original matrix are both less than 1, the conclusion is definite that ultimately it is going to shrink. But in the first iterate it does not shrink, it expands for some time and then shrinks. In the second iterate it will, what is the conclusion? Without actually doing the mathematics, can you conclude how is the second iterate going to look like? It is going to look like a ellipse, an ellipse which is okay. Ultimately, when everything dies down, what do you expect? Things to come to this axis, because this is the eigenvector of the original matrix, but it is going to shrink along that. So, what we expect is that slowly this will come down to the x axis and then is going to shrink. So, in the next iterate you expect something like this to happen. Next, okay, by logic that is what follows. So, intermittently you may see a expansion.
So, first of all, those values are wrong.
Okay, what is that?
1.77 and 0.11.
Fine, no problem. 1.77 and 0.11. Still the conclusion remains intact.
And so, why is the direction is changing?
No, initially if you calculate the eigen directions, it will not be the same as the eigen direction that you calculated here. So, initially it will start from that eigen direction, but ultimately it has to converge onto this eigen direction. That means slowly it will be more and more slim ellipse. Why slim? Because in the two directions there are two different contractivity factors. This one will contract fast. In this direction it is expanding. So further what will happen? It will become thinner and thinner, and finally in that direction it will converge. Okay. Somewhat counterintuitive result, but this is not very peculiar though, because it is not always necessary then that this will happen if the two eigenvalues are equal. Suppose you slightly perturb it, what will happen? The two eigenvalues will not be equal, but still this conclusion is pretty much strong. You see, 1.77 is quite large, 0.11 is quite small. If you slightly change it, this will slightly change, but the conclusion will not change. That means even if the two eigenvalues are both less than 1, the ellipse may actually expand in some direction intermittently and then contract. Is that clear? Clear?
Why were you trying to find this A transpose and then eigenvector and eigenvalue?
Because we are trying to conclude something about the resulting ellipse. Because without that, ultimately what will happen? If you have only this, can you conclude anything about the ellipse that will result from one iteration of a circle? Starting from a circle, after one iteration, where does it land?
So then for a 2x2 matrix, we have some lambda, we have two eigenvectors, we have two eigenvectors and we have two eigenvalues.
Yes.
From that, what we conclude?
We conclude that, okay, let me repeat the question for his sake, for the audience's sake. His question is that supposing you have got a matrix A, B, C, D, and it has two eigenvalues lambda 1, lambda 2, and naturally two eigenvectors u1, u2. What do they say? Right? What do they say? They say that ultimately, if you if this is a fixed point, and if you start from a circle, then ultimately it is going to have this. Suppose this is greater than 1 and this is less than 1, expand along this direction ultimately after many iterations. Ultimately it is going to look like a line, and that line is aligned along u1, but that does not mean it will start like it will go like this. It will actually go like this. You will start from there, ultimately it has to go like this, so it will go like this, then it will converge. This particular behavior is to be captured only by looking at the matrix A transpose. Clear? Otherwise, what will happen? You will tend to conclude that right from the beginning it expands in the direction of the eigenvector. No, it does not. It does not, except for the cases where the matrix itself is symmetric. Clear?
Sir, in the theorem we have stated that we will be starting with a disk for a circle. So, if the starting point is the first iterate, that is the first ellipse, then what
Then it's a bit more complex, bit more complicated. That means the theorem is stated based on an ellipse. So, what did we do? We concluded something from the theorem regarding the first iterate from the circle, and we also concluded something from our idea of dynamics that ultimately it is going to converge into that direction, and from there by logic we concluded about the intermediate steps, but really this theorem does not talk about the intermediate steps. It does not. So, what we have to do? You either need to numerically do these iterations and see how it moves, how it changes. It will be good exercise to do that. Very easy to do with MATLAB. Very easy to do with MATLAB. But normally the theorem talks about the first iteration. How does the ellipse look like? Okay. Now, if you have this idea that it is going to turn into an ellipse, that idea can be used for various purposes. For example, whenever we talk about the contractive direction, expanding direction, we need to use these ideas. But before that, you have already concluded this was sort of a clarification that I needed to give, but I will use these results later. But let us come to the issue of what we started off with in the last class. How do we characterize a chaotic orbit? Look at the screen. Here we have a chaotic orbit. You know that this is the attractor for the Henon map. It is a chaotic orbit. Suppose I want to in some way quantify this characteristic given as a number. This is this much chaotic, or some number that will distinguish it from a periodic orbit or other kinds of orbit. How do I obtain such a number? One very simple thing that one can do that follows from what we studied in fractal geometry. This is a fractal after all. This is a fractal, and how are fractal objects characterized? By their dimension. So, one simple way to characterize such an object is simply to obtain its fractal dimension. And the fractal dimension is essentially, there is another name that goes with the concept of fractal dimension. It is called the box counting dimension, because you really have to count boxes. So, in that case, what do you have to do? You have to overlay the orbit with boxes. Say this is the orbit, and you have to overlay with boxes, and you have to count the number of boxes and then progressively make it smaller. That is what we did. Your size is then epsilon size, and then progressively make epsilon smaller. Okay. And what was the concept of the dimension? 1 by epsilon as limit. That was the concept of the dimension. So, here also that will remain the concept of dimension. That means, we can find out the dimension of a chaotic orbit. If this orbit happens to be periodic, what will be the dimension that you obtain? Say is a period 4 orbit. Period 4 orbit means here there will be 4 points only. What will be the, if you do the same procedure on that set, what will be the number you obtain? Ultimately it will go to 0. No, not epsilon is equal to 4. There are 4 points only. Imagine the situation, you have 4 points only. Initially there will be, say, all 4 filled up, but then if you further keep on subdividing it, there will be many boxes that go out. Ultimately these 4 will be contained in a infinitesimally small number of boxes, n tending to 0. As a result, this d also will tend to 0, while that will not happen if you have a chaotic orbit. The character of the chaotic orbit, as I told you when I was sort of intuitively or by a hand waving argument, I did not rigorously define ergodicity, but I said that a ergodic orbit is one that visits many parts of the phase space. If that happens, then the dimension will not be a integer dimension, 0 or 1 or whatever. So, in this case, for example, your if you do the same procedure for the this map, how will you actually proceed? Suppose here is your chaotic orbit, and you will first start from a box that encloses the whole thing, divide into 4 parts, further divide into 4 more parts like this, further divide, and so on and so forth. That is how we will proceed. And at every stage you will count the epsilon, and you will also count the number of boxes that are required to cover the object, that is n. Now, when you do that, you notice that the epsilon is reducing by half at every stage. Epsilon is reducing by half. That is why, even though the definition of dimension is given by ln n by ln 1 by epsilon, often it becomes more convenient to express it the same as log 2 of n log 2 of 1 by epsilon. Actually the same thing, right? Actually the same thing, but it becomes often practically convenient to write it in this form. So, when you actually have to do it, you often will have to express it in this form to make your life more simpler, because you are actually subdividing by 2 the boxes. For example, for this specific map that you saw on the computer screen, in this case if you do the same procedure, you will get this kind of numbers. What actually is done, you have you draw a graph. In that graph, the log 2 of 1 by epsilon is plotted in the x axis, and the log 2 of n is plotted in the y axis. Okay. What do you expect? It will be a straight line, yes. So, it will be some kind of a straight line, and what is the dimension, the slope of it? No, the slope is the dimension. It might not be 1, it will not be 1 in this case at least. That is exactly why this is a fractal. If it had been 1, it will not be a fractal. So, the procedure of actually obtaining the fractal dimension is to plot a graph like this. So, as you slowly reduce epsilon, you plot a graph and you obtain a straight line. If you do not get a straight line, you know that your procedure is not accurate enough as yet. When can that happen? When can that happen? If your step size are yet too large, or it has become too small. Imagine that ultimately you have on the computer screen something that is generated by pixels, and if you go on reducing the epsilon lower than the size of the pixel, then what will happen? It will be meaningless. So, in this case you will get something that is away from the straight line. That is why it is necessary to draw the straight line, because then you know that I am on the right track. I can get this slope.
Sir, but the slope will be constant once we move up higher, because then epsilon tends to 0.
So, you actually have to obtain the asymptote. If it goes like this or that, ultimately you have to take that part.
It depends on the number of iterations I am taking.
Yes. So, ideally you should take an infinite number of iterations. Physically, computationally that is not possible. So, you have to take a large number, that is all. But you will notice that there is a practical difficulty of this algorithm the moment you imagine how you would like to code it. Ultimately, this has to be coded. You would not like to go on counting physically 1, 2, 3, 4, 5, 6. You cannot do that. Ultimately, you will have to create some kind of bins, boxes, and find out how many iterates fell into each box. For 2D, that is not a big deal. But there is no reason to imagine that a map will always be 2D. There can be 3D maps. If you have a 3D map, and if you want to subdivide each side into say 100, how many boxes would you need? It is a huge, and that many boxes, how do you really code it? Can you imagine? It is going to give a lot of trouble when you actually want to code it, because that will require this many positions to be created, and that many, then those have to be incremented, when computationally that becomes inefficient. Imagine 4D maps, unmanageable. That is why for simple things we do use the fractal dimension as a measure of chaos. Simple means at most 2D, but if the dimension is larger, then it becomes convenient to do something else. What that something else is? There is another thing called this was the fractal dimension, equivalently called box counting dimension. There is another measure called correlation dimension. Now, what is that correlation dimension? Essentially, this is a collection. If you look at the computer screen, you will see that this is a collection of points, and each point is falling in different locations here. Each point is occupying a different coordinate. But then, if I ask you what is the distance between this point where my cursor is and another iterate, obviously that could be smaller than a specific given distance r or larger. If I ask you how many points are there in that chaotic orbit within a given distance r from a point, how many pairs are there? How many pairs are there that are situated within a certain distance? What actually are we measuring? Yes, we are measuring correlation in some way, but notice the difference, conceptual difference with the box counting dimension. in the box counting dimension we are not distinguishing the density of orbits. If a box is filled, it is filled, that is all. How many are falling in each box or how dense are parts of the orbit, those things are not really being accounted for. But the moment I ask, okay, how many pairs can I find in this whole orbit, how many pairs of iterates can I find in this whole orbit that are situated at distance less than r. If it is some very dense in some parts, it will be measured by that. Okay. Now, let me define the number, the correlation C as a function of r is that distance is limit n tending to infinity number, I hope you know that hash represents number, the number of pairs W1, W2, these W's are not meaning IFS, this is that just iterates, such that W1, W2 in the orbit Sn and W1 minus W2, this is the distance is less than r. Do you understand what I wrote? I will repeat, let me write the denominator also. Number of pairs so, in the denominator the total number of pairs, pairs W1, W2 where W1, W2 are in that attractor. In the numerator those pairs of W1, W2 which are in the attractor, but which are also whose mutual distance is less than r.
So n is the number of iterations.
N is the number of iterations. Okay. Now, obviously, if you make large r very large, then this will be more or less equal to 1, because if r is very large, then the numerator and denominator will become equal. R is very small, say 0, then obviously it will be 0. So, it is a function that depends on r. Then the correlation dimension S is given as limit r tending to 0 log C, the function of r, divided by now this number will actually converge. This number will actually converge, and it so happens that it converges to a value that is reasonably close to the fractal dimension, not exactly equal to fractal dimension. It is also a measure of the character of the chaotic orbit, but it also incorporates within it the idea of the density of points. In some part it is more dense, in some part it is less dense, and that will make a difference in the correlation dimension, while in case of the box counting it only sees which parts are covered, which parts are not. Is it clear? Well, in this case how will you actually measure it? Notice here there is no question of box counting, and therefore there is no question of creating 1000 to the power 3 number of boxes. That computational problem is completely overcome. What do you have to do? Start from a point. How many total points will be there? How many total pairs will be there? If there are total 1000 number of points in that orbit, suppose in this orbit there are 1000, How many pairs are there? It will be, there are 1000 points. From each point, how many points distance can be measured? Not itself. So, times 999, one less, right. So, these many pairs will be there. Okay. This many pairs will be there. So, start from 1 and find out how many are less than r. So, collect them into this, go to the next one, find how many. So, it is actually, it does not require that much of memory. You simply go on measuring this and putting it in a bin that counts only the numerator, that is all. Computationally, therefore, this is far more simpler. And since it yields a value that is indicative of the character of the chaotic orbit, this is a good measure. And here also the procedure will make a graph in the x axis. It will be, again, if you are reducing r by 2's, that means initially r was covering the whole thing, then you make half, then you make half of that, then you make half of that, it will be convenient to express it in log 2. So, log 2 of r, and here it is log 2 of, and what do you anticipate? It will again be a straight line, and the slope will give that. All right. So, that is another measure of chaos. That means, how chaotic it is, or the character of a chaotic orbit, as you have already seen that as you change a parameter, the chaotic orbit does not really remain the same. It remains chaotic, all right, but it does not remain the same. For some parameter value it was 2-piece chaotic orbit, for some parameter value it was just, it became 1 piece, for some parameter value it was a very small but chaotic orbit still. Those things can be distinguished, differentiated and characterized by means of the correlation dimension, which is easier to compute than fractal dimension.
When we are calculating CR for small r, you are saying it is going tending to 0, right?
Yes.
Then we are calculating dividing by log r. For small r, it is going to minus infinity, right? So we are dividing.
Both are going to minus infinity. So
Yes.
CR is also going to minus 0 and R is also going to 0.
Yes. So, this we are talking about the ratio. How, so, this ratio is actually, both are, the numerator as well as the denominator are changing. Obviously, you are not taking to 0, that is a fictitious situation. You are slowly starting from say 1, then you are changing to half, then you are changing to 1/4, then you are changing to 1/8, and so on and so forth. You will go at most up to some 8 or 9 steps like this, and calculate the slope, that is it. That is computationally more tractable, that is my point. So, if you are asked to actually characterize a chaotic orbit, this is a more tractable thing to do. Okay.
Sir, is there any relation between the original dimension, the box dimension, and this?
Not directly, not directly. You might imagine the distinction as, if the attractor is, that means everywhere in the attractor has equal density, then they will become equal. But if they don't, then there will be some difference between the two. Clear? Apart from these two, one is box counting direction, the dimension, another is the correlation dimension. Apart from these two, there is another measure of dimension which is often used, but that is related to the Lyapunov exponent. Lyapunov exponent is something already done, right, but in relationship to continuous time systems. Now, we have to do it in relationship to the discrete time systems. It is not exactly the same thing, but since time is coming to a close, I suppose it will be good to cover that later in the next class. Fine. Is there any question on what I did today?
This n number of iterations, what is this? What number of iterations?
Yes, the number of points on the orbit, number of points that you have taken on the orbit, and then you are going on applying the procedure. So, there is some number you start with.
So when we are shrinking the box size, is it necessary to shrink it as small as every point?
Normally, no.
So in that
If normally what happens is that if you see that it is asymptoting to a straight line, then you know that we are through.
So in that case, if the density is larger, then the correlation dimension, the method should be more computationally intensive. Because if there are lots of points, the box size.
No. After all, you are calculating the distance to all points, and then finding how many are falling within R. But what are you doing? You are starting from a point and going on calculating. You are not requiring that much of memory. That is what the computational advantage is. Okay. Fine. That is all for today. We will continue with the next class.